So a little more info on solutions. This is to follow up part 1 of the Colligative Properties Lab and precede part 2 of our Colligative Properties Lab. Initially, let's revisit some of our underlying concepts with solutions. In this first example here, we'll start out with something that's pure solvent. Given that it's pure solvent, the mole fraction of solvent we'd have present here would be 1.0. We have a saturated system that's reached equilibrium, and we've established our vapor pressure for the pure solvent at 25 degrees Celsius. For purposes of our example, we'll say is 300 millimeters mercury. When we make a solution, we're now going to have some solute particles present in our solvent. In our example, when we count the particles, 4 particles out of every 10 are solute, so the mole fraction of solute would be 0.40, leaving us with a mole fraction of 0.60. Now, because we're at the same temperature, with fewer particles in our solution, or fewer fraction that's solvent, fewer particles become gaseous at the same temperature. So our vapor pressure in the solution is going to be lower than what it is for pure solvent. In fact, the vapor pressure will be 6/10 of what it is for pure solvent. And 6/10 of 300 millimeters mercury would give us a vapor pressure for our solution of 180 millimeters mercury when at the same temperature as what we have for our pure solvent. Let's connect our observations, what we see with solutions, to a phase diagram. In our previous example, we had a temperature of 25 degrees. And the vapor pressure would be when we have the liquid-gas equilibrium. So it would fall, any vapor pressure at a specific temperature would fall along the liquid-gas equilibrium line in a phase diagram. Now, one thing observed is that at a given temperature of, say, 25 degrees, the pressure or vapor pressure of a solution compared to pure solvent is always going to be something a little bit lower. And that'll remain true at any temperature that we may pick. We're going to find that the vapor pressure of solution at a given temperature will always be lower than what it is for a pure solvent at the same temperature. And what develops is we get a separate line representing solution compared to what we see for our line for pure solvent on a phase diagram. Now, in our phase diagram, we'll notice that at any given temperature, the vapor pressure of pure solvent will always be greater than what we see for the vapor pressure of a solution. Now, another observation on our phase diagram is if we look at our normal boiling point of pure solvent, which would come down and be at this specific temperature, and if we look at the normal boiling point of our solution, the phase diagram also shows us that the temperature at which our solution boils is always going to be greater than the temperature that our pure solvent boils at. The gap here from pure solvent to solution would represent what we call our change in temperature boiling for a solution relative to pure solvent. On the flip side, if we go to 1 atmosphere, we get our normal freezing and melting point and our solution freezing or melting point. We drop down to our temperature, we have our temperature of pure solvent, and we can see that the temperature at which a solution will freeze at is going to be lower than what we see a pure solvent freezing at. Our difference in freezing temperature for pure solvent compared to our solution we'd identify as our change in temperature freezing, as the solution freezes at a lower temperature than would our pure solvent. So one thing we can see here is that our solution freezing point is always going to be lower than what we see for a pure solvent freezing point. Now, in Chicago, there's some pretty significant ramifications of this. Why in Chicago, why we spread salt on roads in the wintertime. When salt gets spread on the roads in the wintertime, the salt's functioning as the solute. The water, the snow and such, is the solvent. The solution of salt and water that's created has a lower freezing point than pure water. The solution of salt and water will freeze at temperatures below 0 degrees Celsius, which allows the roads to remain unfrozen at temperatures cooler than it would be without the presence of the salt. keeping the roads safer without ice on the roads at lower temperatures than would otherwise be the case. Another type of solution we'll take a look at is a type of solution where we have a gaseous solute. Something we're familiar with, a gaseous solute, would be whenever we have any type of carbonated beverage. In this case, the CO2 gas is the solute, and it's dissolved in a solvent, which would be water, serving as the solvent in a carbonated beverage, where we have a gas as a solute and liquid water as a solvent. In a carbonated beverage, before the bottle is opened, there's an equilibrium. We have CO2 that's dissolved, or aqueous, in equilibrium with CO2 gas that's in a little bit of space at the top of the bottle. The CO2 in that small space in a sealed bottle is under a very high pressure. It's that high pressure of CO2 that essentially forces the CO2 gas into the water to create the CO2 and water solution. Now in this solution, again, the CO2 gas is our solute, the water is the solvent. Now if we focus on that small space, inside here is a pressure of CO2 gas on top of the liquid, and this pressure here is much greater than what we have the pressure on the outside of the bottle. That's what essentially keeps the CO2 in solution in the form of aqueous CO2 inside the bottle to keep the beverage carbonated. However, one thing we've probably all seen is when we open the bottle on something that's carbonated, typically upon opening the top we'll hear like a sound, and what that is CO2 gas escaping from the small space at the top of the bottle. When that occurs, we'll typically then see CO2 gas bubbles start to form in the beverage as the CO2 is no longer quite as soluble and the solute starts to leave the solution, and we get the fizzing at the top of the bottle, which is evidence of the CO2 coming out of the solution. In fact, if the top is left off of a container over time, the beverage would eventually go flat, which is an indication that all of the CO2 solute has now left the solution, leaving just pure solvent behind. Got a few more things to cover regarding solutions, both as a follow-up to part 1 in the lab and leading into part 2. Now, one thing that can occur with a solution, when a solution starts to boil, as we did in the first part of the lab, it was necessary to promptly measure the temperature. So one thing you might have noticed is as a solution boils, we see these bubbles forming, and also we would see steam coming off over the top of the beaker. Now steam is H2O in the gaseous form. In our solutions, the H2O is serving the purpose of being our solvent. So what's happening is, as the solution boils, solvent starts to leave the beaker. So as the solution boils, solvent is leaving in the form of steam. However, the solute particles remain behind in the solution. In fact, you probably noticed this if you ever set out something like, say, a container with salt water, the water evaporates, it'll leave the salt crystals behind, dried out in the beaker or container. Now, the implications of solvent leaving but solute remaining behind is that the molality or concentration of the solution will begin to change. Recalling that molality is moles of solute divided by kilograms of solvent, the moles of solute is remaining constant as the water leaves the container as steam, but the kilograms of solvent starts to get lesser as the solvent is leaving in the form of gaseous water vapor or steam. Consequently, because our denominator here is getting smaller, the size of the molality will go up, which is increasing the concentration of our solution. Therefore, what's happening is as time passes, the mole fraction of the solute is increasing because there's an ever lesser and lesser amount of solvent present, so the mole fraction of solvent goes down. The result is the change in temperature boiling will increase as time goes by. As the solution gets more and more concentrated, the water will boil, the solution of water and solute will boil at an ever higher and higher temperature. Now let's connect this to something that's known as a phase change graph or diagram. In our phase change diagram, initially we're going to start out with water in the liquid form. As it sits on the hot plate and time goes by, what's going to occur is the temperature of the water is going to increase. Eventually, when we hit 100 degrees Celsius under normal conditions, we'll see bubbles form in the water and boiling starts to occur. At this point in our phase change diagram, the graph would plateau and level off and remain constant at 100 degrees Celsius. As during the phase change, the additional energy being provided by the hot plate is causing the liquid to gas phase change as the intermolecular attractive forces are being broken apart by the energy added by the hot plate. Consequently, we see that the phase change diagram remains constant at 100 degrees while the phase change is taking place. Now let's change our picture slightly. We now have a solution. We have some solute particles X. Now what's going to occur as time goes by, we'd see the solution warming up. However, boiling for the solution is going to occur at some temperature higher than 100 degrees. Now as time goes by and our solution boils, solvent is going to start to leave our solution. And what we'd see for solution, instead of a plateau in our phase change diagram, is as the solution boils, this line would show a gradual increase as the temperature continues to increase